Second speaker of this session is Chris Jenkins, and he's going to talk about encodings of Mendler-style coinductive types in Cedille, and I think has quite a different take to the keynote speaker on what type of look like. So I'm looking forward to this.
All right, thank you very much. So yes, my name is Chris Jenkins. I'm from the University of Iowa, Department of Computer Science, along with my co-authors Aaron Stump and Larry Deal. And I'm going to be talking to you about our paper today, Efficient Lambda Encodings for Mendler-style coinductive types in Cedille. So to begin, just a quick review of coinductive types and their lambda encodings. Coinductive types or quadratic types serve to classify possibly infinite objects, and we understand them as coming with a set of destructors for making observations, a collection of generators, a choice of generators for their production, also known as co-recursion schemes, and we desire productivity of these schemes, meaning that all finite observations we make of them with destructors are well defined. Lambda encodings are an identification of the codata type with a particular co-recursion scheme. So your codata terms are lambda expressions, and your types are defined impredicatively. So you also hear the terminology impredicative encoding. Now, productivity for a given scheme comes for free if the corresponding encoding to that scheme is definable in a total type theory. So why not adopt encodings in settings where this matters, such as in total functional programming or within interactive theorem provers? Historically, lambda encodings for inductive types have faced several difficulties, namely those of efficiency and also of logical expressivity, and there's a similar account for the encodings of coinductive types as well. So considering the case of streams, where we're thinking of efficiency in terms of overhead in the number of observations made, for the church encoding, each use of a constructor incurs an additional linear overhead, and that's because constructors will trigger the regeneration of code data. For the Perigo encoding, there is a flat linear overhead cost because every observation you make involves an additional case distinction. Again, this is just for the case of streams. The overhead can be much worse for other coinductive types, in particular ones where the signature is defined, say, with an inductive type, so certain nested constructions. Now, inefficiency and lack of induction and coinduction in the calculus of constructions, that is the matter of logical expressivity, motivate the development of the calculus of inductive and coinductive constructions, where primitive data types are added to the theory. But there is a little bit of a trade-off here. Primitive data types with induction swell the trusted computing base. If you have data type declarations within your kernel theory, this means you have to involve positivity checking. If you have fixed point notation for recursive and co-recursive functions, this means they have to do termination and productivity checking. Finally, if you want to support more expressive schemes, this may require further changes to the meta theory. And so an alternative might be to revisit lambda encodings and to try to repair the issues that we just addressed. And this is the project of Cedille, the calculus of dependent lambda eliminations. It's a formally small extension of the Curry-style calculus of constructions that addresses the foregoing issues for lambda encodings, namely that 1, induction is derivable generically for many encodings, and 2, it's possible to define certain very efficient encodings for inductive types. Cedille is a higher level language that has special syntax for inductive types that gets elaborated down to the lambda terms and types in the core theory Cedille. So the question, of course, at this point is, well, what's the story about coinductive types? And that is the subject of this talk. We're presenting a Mendler-style of encoding for code data in Cedille that is generic. It works for any positive data type signature. It's efficient. There is no penalty paid for use of constructors, and it's expressive. It supports a combined course of values co-iteration and primitive co-recursion scheme. What is missing in these results are the matter of logical expressivity, namely that these encodings do not support true co-induction in the sense of bisimilarity implying equality. Indeed, we present in the paper a counter result with respect to Cedille's primitive equality type, but of course, index co-recursion for reasoning is supported, and you can see details of this in the paper. What I want to focus on in this talk is just on how we guarantee efficiency for just the primitive co-recursion scheme. In particular, what the Mendler-style of coding co-recursion is and how it helps, and the two techniques we use to ensure efficiency. One, fairly standard monotone fixed point types, a la Mathieu's, and the other is a Cedille specific technique, proof-irrelevant type inclusions. Okay, so let's take a look at this formulation of co-recursion schemes that the encoding is based on, the Mendler-style. For every classic or conventional co-recursion scheme, there is an equivalent Mendler-style scheme. Now, the advantages of the Mendler-style have been well studied in the past couple of decades, but just as a short summary, it's more idiomatic for functional programmers because you are making your co-recursive calls explicitly in the same style as you would with general co-recursion. And in particular, the Mendler-style formulation avoids the buildup of intermediate structures that occur in more complex schemes expressed in the conventional style. And indeed, the fact that they were avoiding this building up of these intermediate structures just to tear them down during observations is what helps us, what assists us in the efficiency gain. Taking a look at just the simple co-iteration scheme for the generation of streams, in the classic formulation, this is done by taking some type S, which we're going to think of as a state space, and along with this type, we provide two operations. One, H, which is a function that says, given the current state of the stream, tell me what the head element is. And the other, T, which we can think of as a state transition. Given the current state of the stream, give me the state associated to the tail of the stream. Indeed, looking at the operational semantics, which are here described as saying what are the observations defined for the stream generated by coiteration. If we take the tail of the stream generated by classic coiteration, we find that it's what we get when we take the initial state, the given state S, take one step with a transition function T, and then generate the stream out of that. The conceptual leap that occurs in the Mendler-style formulation is how we think of T. Instead of having it be a state transition, we can think of T rather as a stream generator transformer, and one that has this parametric property. So T is now a higher order polymorphic function quantifying over a type argument R. Taking functions of type S to R, where we're thinking of this function as a way of generating streams from R. So R is sort of a stand-in for recursive occurrences of stream A itself. I'm taking such stream generator functions and transforming them to another. Looking at the operational semantics, we see that indeed the tail of the stream so generated is given by taking T, instantiating the type argument R to stream A. We must now provide a function of type S to stream A, but this is of course exactly what the Mendler-style combinator for coiteration gives us. And finally, the given state S. To look at how the Mendler-style formulation helps to avoid the buildup of intermediate structures, let's take a look at the slightly more complex scheme, the primitive co-recursion scheme. The idea behind the scheme is that you want to short-circuit the generation of co-data by returning some pre-made values. So in the case of streams, we might be generating, say, the first 100 elements of the stream, and then decide that the rest of the stream can be given by a stream that was already created. The way that this is done in the conventional formulation is to have T return a co-product, where on the right-hand side, you're still considering the values of type S as the state of the tail. But on the left-hand side, if it's a left injection, then this is our early exit conviction. In the operational semantics, this is done by doing a case distinction on the value returned by T of S. And indeed, if it's a first injection, we just return the given stream. Otherwise, we continue generating. In the Mendler-style formulation, instead of introducing a co-product, we provide the generator transformer another argument, another way of creating values of type R. So now, instead of creating these values from just S, we allow the user to provide, to take given some pre-existing stream A and inject this into the type R. So before I said R is standing in for the type stream A, now we can refine this intuition a little bit and kind of think of R as being a certain super type of stream A. In the operational semantics, again, instantiating the type argument R to stream A, we see that now this additional argument obligates us to provide a function of type stream A to stream A. And of course, this is easily given by the identity function. Noting here, in the case of the Mendler-style formulation, you see that there is still this additional beta redex But in the next section, I'm going to show that even this, a little bit of overhead, can be completely removed in Cedille. All right, so now let's take a look at how this is achieved using monotone recursive types and proof-irrelevant type inclusions. If we were to try to read an imperative encoding off of the rules governing the Mendler-style primitive co-recursor combinator, we would find that we seem to need recursive types, and indeed there's no other known way to achieve this. This is because we want to take the types of the terms occurring in the premises of this rule and use it as a definition of stream A, and wouldn't you know it, stream A would occur recursively in the definition. As a refresher for a type scheme F, a recursive type μF is one such that there exist these two operations, roll and unroll. Roll we think of as taking an F collection of μF predecessors and constructing a successor value. Unroll undoes this, taking some value and unraveling it into its F collection of predecessors. And indeed, by undoes this specifically, we must have the following computation rule, that unroll of roll of T should reduce to T. This is also called the beta law for recursive types. Of course, unrestricted recursive types lead to non-termination in your theory, and the culprits are these type schemes F that have negative occurrences in their type argument. So, of course, we can use a syntactic notion of positivity to recover termination, or what we will be using here is a notion of monotonicity and monotone fixed point types. Of course, the notion of F being monotone in a pre-order is that for any two elements in the pre-order, X being less than Y implies that F of X is less than F of Y. If we want to generalize monotonicity to type theory, we need some way to interpret this less than or this ordering operation and implication. And of course, you can interpret monotonicity in system F already by interpreting both of these as a function space. But for recursive types, this would lead us back to Church encodings. And of course, the problem there is that the beta law for the beta law for these types would not be satisfied. That is indeed a more general statement of the problem of the inefficient predecessor for Church numerals. So the Cedille twist is going to be to choose a different interpretation. For the ordering operation, we are going to use a notion of type inclusion, here written cast ST, which we interpret as saying that every term of type S also has type T. For the notion of monotonicity, we are going to have a listing of type inclusions over the type scheme F, but in a way that's done it's going to be done in a proof-irrelevant fashion. So let's talk about this notion of erasure and proof-irrelevance. So again, Cedille is Curry style. Type annotations are external to the real term language, which in our, philosophically, which we view as the untyped lambda calculus. And so all of these are erased. Indeed, definitional equality is defined up to erasure. So this polymorphic identity function over on the left-hand side and this identity function on T on the right-hand side, both erase away, to the untyped lambda calculus term lambda XX. One of the ways in which Cedille extends the calculus of constructions is that not only type arguments, but term arguments to functions can be irrelevant also. This is written here as T. Little t has type T prime open arrow T to mean that T is a function taking some T prime argument, but the T that it returns doesn't depend at all upon the choice of the given argument. Syntactically for applications, we write that we write application of a function to its erased argument with a hyphen, and the erasure of this expression is just erases away to the function itself. So the argument that occurs in this application disappears. Type inclusions, cast ST, are a derived notion in Cedille, but for brevity, I'm presenting them here axiomatically. You can see full definitions in the appendix. For the purposes of the talk, I just want to focus on these two properties: the derived elimination form and its erasure. So if I have a witnessed that there is an inclusion of the type S into the type T, then I can convert this into a function from S to T, of course. But what's important about this rule is that the use of the function does not depend upon at all on the particular choice of the witness. Indeed, the elimination form here erases to lambda XX. And of course, the idea behind this is that if every term of type S has type T, And if I want to write a function that converts between the two of them, I take some given term of type S, and then I just return it because it already has type T. So the takeaway here is that type inclusions are computationally irrelevant. Then we can define monotonicity, again, as a lifting of type inclusions over type schemes and get this derived elimination form and its erasure. Elim mono gives us a function of type f of s to f of t if we know that f is monotone and we have a witness of the inclusion of s into t. And again, this monotonicity witness is also erased, and the erasure of the elimination form elim mono is just lambda xx. So the takeaway here is that monotonicity witnesses are also computationally irrelevant. Finally, using standard techniques, we can define the recursive type former rec with a constructor and destructor. What we see here is that both roll and unroll do require proofs that f is monotone. However, their definitions do not depend upon the particular choice of proof. And indeed, that's because roll and unroll witness a two-way type inclusion between the types f of recf and recf. They both race away to the identity function, and as a consequence, the beta law is trivially satisfied because then the statement is a composition of identity functions, operates extensionally like the identity functions. All right, so now I want to take a look at the generic encoding, not getting too much into the details, but just really pinpointing where the technique is guaranteeing us efficiency. So by generic, I mean parametric. We're working with a type scheme f and a witness that f is monotone. For simplicity, the type definitions I'm showing you here for the encoding have had the support for course of values co-iteration stripped out, but you can again see the paper for the full definition. The first type definition is coalgebra. Of course, it's the generalization of the shape of the scheme for co-recursion. S is still our type parameter representing the state space, the given state space. But C is now the parameter which we're taking our fixed point. This is still a polymorphic function quantifying over type arguments R, types R. Before we had highlighted before a function of type stream A to R when we were looking at streams. Now we're talking about an inclusion of the codata type into R that is given as an erased argument. So again, proof irrelevant. Then we can define our codata type new using recursive types and this existential encoding. If you have not seen this before, this is a standard way of defining greatest fixed points in type theory impredicatively. And noticing here that this type scheme is positive in the type argument C, we can see that we can define roll and unroll. We can use roll and unroll to define the generator and destructor, unfold m and out m, satisfying the following typing and computation rules. In particular, in the computation rule, I have that if I make an observation with out on the stream generated by unfold m with C and S, I take my coalgebra C, instantiate the type argument R to new. My obligation is now that I must provide a proof that new is included into itself. And of course, this is easy because every type has by an easy lemma, every type is included into itself, followed by the handle for making co-recursive calls and the given state. But notice that here below, what we had before was an additional application to lambda xx, and now is an argument to, this is a application to an erased argument. So there's indeed no overhead for primitive co-recursion here. But that's not the only thing we wanted to guarantee, right? We also wanted to make sure that the use of a constructor did not introduce any overhead either. So we can we take a look now at the definition of nim. It has a type f of new to new. In order to define it, we do use the generator unfold m, choosing as a state space the type f of new, introducing our assumptions of type argument R and inclusion and G. G has type f of new to R, and this again is our handle for making co-recursive calls. If we were to use G in order to construct a value of type f of R, then we would have failed in our goal, because this would mean that we were co-recursively regenerating data at every observation. So instead, we take a different approach. Our obligation, again, is a function of type f of new to f of R. We have a proof, a witness, that there's an inclusion of new into R. and a witness that the type scheme F is monotone. So that means that we have an inclusion of F of nu into F of R using the derived elimination form in lim mono. This gives a function of the appropriate type that erases away to lambda xx. As a consequence, the following operational rule, or 1/2 of lambda x lemma, if you're familiar with the statement, out m of in m of t reduces to t for all terms t. There is no regeneration of codata, which is what you would see in the church encoding, or if we were to use G here in this expression. And indeed, there's no traversal over the type scheme F with fmap, which is what you would see in most encodings and pretty much any other type theory that does not have equivalent notions. And again, I mentioned at the outset that if F, say, if your signature for your codata type was a list, then fmap would be a list traversal, and then every observation would, could be quite expensive potentially. But here, none of that happens. It's just an identity function, a type coercion function. So there is no penalty for the use of constructors at all. So in conclusion, we presented a generic derivation of codata in Cedille supporting an expressive co-recursion scheme efficiently. In order to do so, this required a different approach than what we have used previously for efficient inductive types, namely leaning on monotone recursive types a la Matis. The termination guarantee, so there is a proviso here. The termination guarantee in Cedille is somewhat subtle. It holds for closed terms, which can be assigned a function type. And if you're hearing that and thinking, well, wait a minute, well, then it can't be a true type theory. Well, yes, this is a bit of a caveat, but the condition does hold for all closed terms, data and codata, all closed terms which we would consider as data and codata, but computing with open terms is in general unsafe. Indeed, the feature that we use to guarantee efficiency, one of the axioms in Cedille, contributes to this proviso. Now, for future work, we are actively working on an encoding that supports co-induction up to an equivalence relation that's derived from binary parametricity, rather than trying to do this up to Cedille's primitive equality type, which is what we use in the counterexample. That's more of the semantic side. On the syntactic side, we're looking at designing a nice surface language for codata that involves co-pattern matching and using coercive subtyping to infer the insertions of these type inclusions. But the Mendler-style formulation does help to bridge the gap between syntax and semantics because productivity checking is reduced to type checking while maintaining a familiar style of making explicit co-recursive calls. All right, and that's my talk. Thanks.
Thanks, Chris. Okay, I'm just going to see, are there any questions in Zulip? Yes, there is. Okay, there's one silent question from Pierre-Marie. He says, can you give an intuition for the example that bisimilarity is distinct from equality? Is it due to the use of continuation parsing style in a nonlinear way, i.e. availability of control operators in Mendler-style?
Yeah, so I don't think that it has much to do with that. It has more to do with the fact that Cedille's primitive equality type is anti-extensional. So if you're, the ideal notion of equality for co-inductive types is equivalent behavior. But of course, you can have two state machines, say, that have different internal configurations that generate the same behavior. But if you state that two terms are equal up to Cedille's equality type, this is literally intentionally equal. So this is how arises the counter example.
Okay. Any more questions? Tarmo has a silent question. He says, thank you for the very clear talk.
Thank you.
Can you comment on what is the status of Cedille's very powerful meta theory today? What has been proved about it, and what has been proved with pencil and paper, and what has been proved formally? I think he means mechanized.
Right. So we are currently working on we have a project involved of formalizing Cedille in Coq, as well as a translation of a subset of Coq into to Cedille. But there are no results, results currently to present as far as mechanization. Concerning the meta theory of Cedille, of course, it is consistent as interpreted as a logic, and we have the termination guarantee as well. That is not, of course, it's not complete for it does not hold for all open terms, but it does hold for closed terms. So these are the essential to meta theoretic properties.
Okay. I guess following up on that, I have a maybe slightly higher level question, which is you get this nice performance improvement with these encodings, no overhead at all. That's great. But what, if anything, would you say you're paying for in terms of your ability to reason about programs?
So I suppose, yeah. I'd say, are you asking more? So you're asking more like, what do you pay for having to do this within the setting of Cedille itself, or anything particular about the encoding?
Well, say if you want to prove some property about a Cedille program, is it made any more difficult by the particular kind of encoding you're using, or is that are you sweeping some details under the hood by using these fancy encodings, or does it just work out just as well as it would if you were trying to formalize the same thing in Coq or something?
So I would say that for the choice of the particular encoding, it works out. It works out quite well. The more, and this is because the more you rely on erasure, the more essentially, you know, when you're proving something about about a program in Cedille, you know, you're really talking about the underlying untyped lambda calculus term, and the more you lean upon erasure for your operations, the simpler the underlying encoding is. So there are, of course, you know, Cedille, the meta theory lacks large eliminations, so there are limitations to working within the theory itself. But as far as the encoding is concerned, I can't say that I've encountered any like real technical difficulties with this. It's actually quite simple.